Hi, welcome to Cloud OnAir. These are live webinars that Google's Cloud is hosting, and we're doing them every Tuesday. My name is Brian Sullivan. I'm the Senior Program Manager with Google Earth Outreach. I'm here with...
I'm David Cruz. I'm the Director of Research at Global Fishing Watch. And today we're going to be talking about how Global Fishing Watch uses Google Cloud. Throughout our whole presentation, there'll be Googlers standing by to answer your questions. So you can just type them in on the platform and they'll be ready to answer them. So let's get started.
Great. So within Google, we have a team that we call Geo for Good. And our goal is to take on some of the world's most pressing issues around the environment, conservation, public health, and other humanitarian issues. And fishing is actually one that really relates to a lot of these issues. So when we think of fishing, this is what we traditionally think of. It's a quiet morning, we're out there, and we're with nature. But the reality of industrial fishing is actually quite different. And it's something that, as a society, is very difficult to comprehend. This is an example of a moratorium in China, where for 3 months they close fishing so that all the fish can recuperate and rebound their stocks. But at the end of 3 months, this is what's coming for you. And you can count all the boats that are in here. And once you get a sense of how big you think this is, you can zoom out a little bit more and get a better extent of just what global fishing looks like and the pressures that puts on the environment and our food. You can zoom out one more time, and you can really start to understand how big this is. Now, we have these photos because a photojournalist was out there, and they set these up. But how could we zoom out and see the entire world? What would that look like if we could truly understand the extent of global fishing? That's what Global Fishing Watch is enabling us to do. So I'm going to switch over to a live demo now to show you something that's free for the entire world, and anyone is able to go online and start to understand how much we're actually fishing our oceans. Now, the first thing you'll see is all these blue dots in the middle. And these are our fishing algorithms that are determining where we're actually seeing fishing. And this is an interactive map, so I can pan around and I can zoom in to different areas. And one of the things that we'll see is that there's some spots in the middle of the Pacific that are wide open and we see lots of fishing, and then we see other holes in these where we have things like marine protected areas or country boundaries that are dictating whether or not people are allowed to fish in these regions. And you'll see very different patterns right along the country's borders versus out in international waters where people are deciding who has the right to fish there. Now, the same way we can see this macro view and zoom all around on this, we can actually go in and see an individual vessel. And so what we'll be doing now is you'll see a pink line, and that is going to be an individual vessel, the Val Matal. Oh. Ah, the joys of live demos. And so as we play this forward, you'll be able to see an individual vessel. And so out of this pink line in here, we can see how that's changing. Let's go into our layers, and we'll go into our activity, and let's turn off all the other background behind that. And now you can see the distinct pattern that a boat makes when it fishes, when it's wiggling back and forth like that versus when it's transiting and it has those straight lines in between. Looking at one more example, we can see where MPAs and other areas like that have been created. Let's go back to this one. Sorry, that was the problem when you switch resolutions. All right, well, thanks for bearing with us on that. But the question is, why does a company like Google look at something like fishing? And so over 1 billion people in the world depend on fish as their primary source of protein. About 90% of the apex, or the largest species, have disappeared within our lifetime. 85% of the world's fisheries are either overfished, at capacity, or recovering. About 1 in 5, or 20% of the world's fish, are considered IUU, illegal, unregulated, and undocumented. And then when we look at this at a global level, this is about a $60 billion market that is really affecting developing countries the most. And that ties down to food security, it ties down to sovereign rights, and a lot of other issues like slave labor that you wouldn't think of initially. So let's talk a little bit about how this is actually working behind the scenes.
Great, thank you, Brian. So I'm David Cruz. I run the research program at Global Fishing Watch, and Global Fishing Watch is a small nonprofit dedicated to increasing transparency in the global fishing industry, and a lot of what we do is using Google tools. I'm going to go into details of how that technology works and how you make those really nice maps that Brian just showed us. The key technology is something called Automatic Identification System, or AIS, that all large ocean-going vessels have to carry. And what it does has a little GPS in it, and it broadcasts the vessel's location so that other boats nearby can see where it is and thus avoid collisions. It's a safety device. These signals, though, are broadcast over radio, and they can be picked up by satellites flying overhead or a network of antennas along the world's coastline. And what we've done at Global Fishing Watch is obtained a global database of all of these AIS messages and then process them. If you plot all of these messages on a map, what you see is, over 1 year, something that looks like this. This is one of my favorite maps. You can see all the world's shipping lanes. You can see where fishing is happening. You can see places near Antarctica where boats don't go. This is all vessels. Only about 1 out of 5 are fishing boats. So now we have this big database, and we have two classification problems. One, we want to identify which of these vessels are fishing vessels and what type of fishing vessels. And two, for those vessels, we want to identify when they're fishing. And so this is where we use Google Cloud. First, let's start with the first problem, identifying what's a fishing vessel and what type. So in AIS messages, they broadcast the name and call sign of a boat. And we've been able to take these messages and match them up to official registries to figure out what type of boat about slightly more than 50,000 of these almost 300,000 vessels are. So that tells us, say, whether it's a tugboat, whether it's a trawler, and so forth. So we have this large training data, and then we have to be able to infer what the other vessels are. Fortunately, boats have very different patterns of how they move in the ocean depending on what type of vessel it is. So here on the left, you can see the paths of a trawler, which is a fishing vessel that drags a net behind it to catch fish. In the middle is the path of a long line, which, as its name implies, sets long lines of hooks that can be up to 100 kilometers long in the ocean. And then on the right is a purse seine, which encircles schools of tuna or another fish with a net and draws them in that way. Each of them has a distinct pattern which you can recognize with your eye, which means we can probably train a model to do the same thing and differentiate them. But to train that model, first we have to process this data and create features for our machine learning algorithm. And we do all that in Google products. So every day we get about 50 million unique AIS messages. And we run those messages, we parallelize those messages in Dataflow. And the first thing we do is something very simple. We just create realistic segments with all the messages from these vessels and get rid of noise such that you have paths that you can work with. There's actually a lot of noise in the AIS that needs to be cleaned up. And then we put that into BigQuery. BigQuery is Google's platform. It's an SQL-like database that allows you to do terabyte-sized queries. It returns very quickly, and it's very useful for all of our analyses. Now we have all these points, and we want to figure out spatial information about each, such as the distance to shore, whether it's in the exclusive economic zone of China or Japan, distance to port. And we do that by taking global shapefiles, such as the one of all the world's coastlines or one of all the world's ports, and do calculations in Dataflow to find out for each position in the world at 1 kilometer resolution, so it's about 30 million points, the distance to the shore and distance to port. We then take those rasters, upload them to BigQuery, and then it's very nice, we're able to do a join, because that's what you can do in BigQuery across these millions and millions of positions to get that spatial information about every single position. So now we have a nice, useful data set in BigQuery, and we want to create features for our machine learning algorithm. We have about 30 billion AIS messages in all. This is on the scale of terabyte. And we continue on Dataflow to do some calculations. For each single position, we calculate 11 different features. These are simple things such as the time between positions, the implied speed between positions of a vessel, how far that is from shore, how far that point is from an anchorage, the time of day. And so now we have some information about all those features, and we want to train a model to identify what type of boat it is based on these features. To do that, we use a common type of machine learning algorithm called the convolutional neural network. This is a type of, this algorithm has actually become very common in image recognition. It's probably very similar what Google Photos uses to identify what's a cat and what's not a cat. And here's how it works. So we're taking, for each vessel, say we have about 13,000 positions, we're going to try to use to identify what type of boat it is. And each of those positions has 11 features, so that's over 100,000 features per vessel. And we run a convolution, a 9-layer convolution across it, which essentially reduces the number of features down to something more manageable, in this case about 2,000, which we can then run across a fully connected network to get 14 different vessel class probabilities. So the output of this is a number that tells you whether or not the neural net thinks the boat is a tugboat, whether it thinks it's a trawler, whether it thinks it's a longliner. This next slide shows how well we think something called the confusion matrix, which is a common tool used for identifying how well machine learning algorithms do at classification problems. It's a little complicated to read, but basically one row of this is all the vessels from one class in our test data, and the column is how many of the boats from that class the neural net thought was in that class. So basically, high numbers along the diagonal is good. That means that vessels from the test data were labeled with the same value by the neural network. And as you look at this, has a very high accuracy on our data set. A lot of the vessels it gets wrong, I've looked at them. Oftentimes they're very inactive vessels, or they're some vessels which have kind of mixed class or outside of these 14 classes. So we do a good job at identifying what's a fishing boat and what's not, and the type of fishing vessel.
So how many boats are you looking at here?
We're looking at, so there's 300,000 vessels overall. In 1 year, across all years, it's actually closer to 400,000 because some boats aren't active every year. And there's about 60,000 fishing vessels active in 1 year and about 70,000 active across all years.
Okay, so it's about 70,000 vessels that are being shown in the public.
Yes.
Global Fishing Watch, and then there's the full 300,000 that we're doing our own analytics on inside.
Exactly. No, that's a good point, right? Because when you look at Global Fishing Watch, you're just seeing the fishing vessels, but in order to identify them, we have to process all of the vessels.
Okay.
So that then brings us. So now we know. Oh, the other thing I think is really exciting about this is that big boats move differently than small boats. So our model can also tell how large the vessels are. This is the length, engine power, and tonnage on the x-axis here is from our test data, and the y-axis is what the model predicts, and does a really good job of predicting how big boats are, which can be useful for all types of studies.
So what you're doing here is you're taking the AIS, which is kind of like a GPS track of the boat, and the only information you have is how fast it's moving and when we're seeing a signal from that. And with that information, you're figuring out how big of a boat it is, how much power it has, and then just like how much it's weighing as well.
Yeah, it's kind of, I think it's kind of amazing, but that's exactly what we're doing.
So it's like Strava for all the world's ships.
Yeah, exactly. Essentially, yeah, and it can tell what's and it's amazing that how much you can tell just based on how it moves.
Okay.
So, which leads us to the next thing, which is you want to know when it's fishing. So now we know what type of boat it is, and you want to look at how it's moving, and you want to say, okay, this is a trawler, and right now we think it has its net in the water, or you want to say this is a trawler, and right now it doesn't have its net in the water, and it's going to port, because you want to say where fishing is happening. And the way we do that is we need just like with the vessel classification, we need label data. So we need to know where fishing. We need to take all the data. We need to take basically all the tracks of boats and label each position as fishing or non-fishing.
Okay.
This turned out to be a lot of work. We had to manually label more than 1 million points. This is a case where grad students are your friend. We partnered with a number of research institutions that helped us with this. And we built a JavaScript tool. You can see a screenshot of it here in something called Pybasa. And you can label, what we do is you look at these tracks of the boat, and we work with fisheries experts to help train us. And you label each position as fishing or non-fishing. We labeled more than 1 million positions. The way we did this largely also was me every day bothering people on Slack and then sending out encouraging notes or critical ones if they were not labeling enough. We did that for 2 months. And then we were able to train our model.
So at Google, machine learning is something that's coming up all the time. And usually whenever someone wants to apply machine learning to a project, the biggest issue is getting training data. And so how long does it take you to amass 1 million points like this?
So we were helped out a lot by the grad student who had basically spent a year doing this. So that was quite helpful. Thank you, Christina, if you're listening. And then it took 2 months to get another few hundred. Basically, she did half of it. And then it took us 2 months to get another half of that through me bothering everyone day on Slack and a team of about 10 people spending each some time during the day. So we calculated that it would take, if we were to do this across the whole data set, it would take us about, I think it was like 400 years to label all the fishing activity.
So you're saying if a human were to do it at the same speed that a grad student would do it,
yes,
that grad student would be working 400 years.
Yeah, and one of the tricky things here is we couldn't, there's a lot of nice tools. I know Google has been developing these to kind of outsource these labeling projects, for creating label data. But we actually had to be trained to do this because we needed to have kind of expert decisions about what's fishing versus not. So we couldn't outsource it in the way we might have liked to.
Oh. So it's a nice example for machine learning where like if a human looks at the track, they kind of have like an intuitive sense of why it's fishing or it's not fishing.
Yeah.
But there's not like a clear formula that you can run the same way on.
And there is to some extent by gear type, but all those rules are complicated enough that it's better to have human judgment put on it. So, and so the output of it is a table like this. This is a view of what's in BigQuery. And the far right column is the NN's neural net score. And it's 1 if we think the boat is fishing and 0 or null if we don't think. So now we have every single one of our data points labeled as fishing or not fishing. And we also think we know what types of vessels they are. So now what we can do is now we can do analyses. Now we can tell stories and make maps. One thing I do almost every day is write queries in BigQuery and then also link up to that using Python. This is a screenshot of an IPython notebook where I have a query that is trying to groups data from a BigQuery table into latitude and longitude to make a grid. I use Pandas library. It has a nice, has a module for connecting up with BigQuery. I take that out into a raster, and then I can map it and do analyses. And so here is a global map of just the fishing vessels while we think they're fishing in 1 calendar year. And this is basically the scientific product of the same thing that Brian showed you earlier and what we're showing on that global map. We can, if I change the way I write that query to query only by specific gear types, I can get a map of where all trawlers in the world are, and you can see they fish along the world's coastlines. They often drag their nets along the seafloor, so they stay close to shore. Drifting long lines, which set those hooks 100 kilometers long out in the high seas. Purseines, which encircle fish with their nets. And so you can see each fishing pattern has a distinct location in the world. So, yeah. In summary, we're taking in an AIS feed from over 30 satellites and hundreds of terrestrial receivers with almost 50 million AIS messages per day from 300,000 vessels across a year, over 6 years of data. We then also, for the training, we're using vessel registries to identify the types of boats, and also the over 20,000 manually labeled track segments, or 1 million positions. We put that all together through the various Google tools, and what we get out is about 70,000 fishing vessels, 14 gear types, 14 vessel types, of which half are fishing types, the size of vessels, when we think they're fishing, and all of these wonderful maps and data that you see available. One thing I should add is that we're trying to make as much of this data publicly available, as well as our code base, so that our machine learning algorithms, which we also run through TensorFlow and Cloud ML, are open source. And you can go to globalfishingwatch.io and find links to those GitHub repos to see how we actually did this. And again, it would take about 400 years for me bothering you on Slack to complete it. We use Google products at almost every step of the way. We use Dataflow, which is really nice for scaling up compute engine instances, so we don't have to worry about allocating all of our resources or keeping too many machines running. BigQuery is how we store a lot of our data and run queries on it. I use it every day. Cloud ML and TensorFlow we use for our models. Cloud storage as well. Apps Engine is used on the map, as well as Maps API for showing off the interactive map that Brian showed you earlier. And then I'll talk a little bit more about Earth Engine, which is another platform used for analysis.
So one of the things about Global Fishing Watch is that it's a partnership now between Google, that was a founding partner, and initially 2 other nonprofits, SkyTruth and Oceana. And now we've stood it up as its own independent nonprofit. So it's been a great opportunity as these projects were evolving. When we were in the early stages of Global Fishing Watch, Dataflow was just coming out. Right. And so being able to give external people alpha access to this to really refine what were the features that we needed, what worked well and what didn't, has been really fun. And so I know BigQuery is one that we have a whole team of data scientists that don't really have the background in systems administration and really scaling massive parallel computing. But by being able to do everything directly in BigQuery, they were comfortable with SQL, and suddenly they were doing these massive analyses that they wouldn't have been able to do otherwise. And
that's kind of a lot of where I sit, actually, because I'm doing a lot of the analyses and working with our engineers who are doing some of the more distributed stuff. It's actually been kind of fun over the last few years to see us kind of move over to these new platforms which are auto-scaling and which are kind of doing the same thing for BigQuery that BigQuery has done for me for some of these, like the Cloud ML and the compute and the data flow. So, because at the end of the day, I don't want to worry about how to scale up all these compute instances and all that. And that's why BigQuery is so nice, because I never have to think about the parallelization. It just does it. And that brings us back to the analysis. I'm saying really what we care about is getting useful information out of this. And so the large part of my job is working with 11 different research institutions in our research program to take this massive data set and turn it into useful knowledge. And we're doing that through over 25 different research projects. We have 10 papers already published, many, many more in the works. And I'm going to give you 2 examples of what we can do with this. One is just simply people are trying to understand how fishing responds to different temperatures. So what you're looking at here is an animation. The background shows sea surface temperature, and then the dark blue is drifting longline fishing activity over the course of 1 year. And you can watch the fishing activity move, and you can watch the temperatures change. Some of our researchers are building models to see how fishing responds to changing temperatures.
So just to make sure we understand, you're saying that near the equator, the water's a lot hotter. Yeah. And so you can actually see like little jet streams and things like this coming off of, that may not be the right scientific term, but you can see currents coming through here and how those temperatures are shifting. And all the wiggling dots in the middle is we're using long line. Yeah. And then down here, this would be much colder water near the poles.
Yeah. And now I'm going to zoom in now to between Australia and Africa. The colors will change. Yellow is very warm, black is cold, and the white is fishing activity. And this is between May and September of 2016. And you can watch and see the fishing activity follow this kind of constant temperature as the gradient moves northward. And it's really cool. And we've been able to look at how this changes between years. And we can now model this. And this is useful for all types of things, ranging from how we manage the oceans now and thinking about where fishing is happening and how to allocate permits, to thinking about how to respond to climate change. And we built this graphic you're seeing here was built using Earth Engine, which is a Google platform for doing very large global raster calculations. And that's what their sea surface temperature model built into it at very high resolution daily that we're able to compare with our fishing activity.
So we're seeing as the waters get warmer and move north, you're saying the fish follow that same temperature.
Yeah.
And then the fishing boats or the predators are following that the same way. And I think there's actually researchers that are looking at like what would be the migration paths for different fish and other species like that as we have sea surface temperatures rising across the board, and then how will other ones be squeezed in and out. And so this is giving new tools for them to look at that weren't really possible or available before.
A second project that's good to highlight is something called Transshipment. So some vessels, instead of returning to port and offloading their fish at port, they meet up with refrigerated cargo vessels at sea to offload their fish. And this is, they do this partially because sometimes it can save fuel, but another reason is that it can also help obscure where the fish was caught and what vessel caught the fish. And this is one way that illegally caught fish enters legitimate markets. It also allows vessels to stay at sea for a very long time without coming into port, which has been shown to be associated with instances of essentially slavery at sea and also other illicit activities. And so our essential goal is to create transparency. Not all of this transshipment is bad, but our goal is to create transparency. We can understand where it's happening, and so we can better assess its activity. If you could imagine, this is basically we have all the positions of all the boats in AIS, and we want to see when two boats meet up at sea, which is basically a cross join between tens of millions of positions, which is an enormous calculation. We do this in Dataflow by gridding the world up and breaking it down into smaller pieces so that we can identify everywhere one fishing vessel meets up with a refrigerated cargo vessel at sea for several hours. And from that, we're able to create the first ever global map of transshipment behavior. So this shows the red dots here show everywhere we see a refrigerated cargo vessel and a fishing vessel meet up at sea. And the light blue dots are places where we see where we think transshipment might be occurring with less confidence.
So what you're saying is, like, if you look in these photos, this smaller boat is the actual fishing vessel, and then that pulls alongside the larger refrigerated vessel or like a tanker, and then they offload everything from the small boat onto the big boat. And so the big boat may not actually be fishing, but it meets up with all these small boats around the area and then brings that back into a central place.
Yeah, and the reason you want to do this is because big boats are more efficient at crossing the ocean than small boats, and so you can save fuel if you do this. But again, it also obscures supply chains.
Okay.
So Brian's going to talk a little more about why this matters.
Yep. So one of the other impacts that we've seen of transshipments is that the same way they'll be moving fish from a fishing vessel onto a cargo vessel, they'll also bring supplies and all kinds of other materials back onto the fishing vessel, so the fishing vessel could stay out for months and months at a time. And the AP did some incredible investigative reporting, and then what they found is that in a lot of these cases, the crew is actually related to slave labor because they're literally trapped on the boat and unable to leave. And so being able to help map out where transshipments were happening was a key piece for helping them to understand where these vessels might be going and how these supplies are going.
And those pictures you saw earlier of those transshipment vessels, those were actually taken from satellites, working with members of Global Fishing Watch, who are looking at AIS data of those large refrigerated cargo vessels and saying, we think there's a boat here, why don't you tell your satellite to take a picture? So it's yeah.
And that's moved on to, I think, the next slide of this. There's another example where in Palau, people were looking at poaching that was happening within a small country in the Asia Pacific. And in many cases, being able to see this as it was happening, they were able to send out enforcement vehicles from the government to pull alongside these. And the New York Times Magazine did a whole piece on the story of how a lot of these developing countries are being taken advantage of by more developed and industrial fishing countries and companies to exploit this. And so adding transparency to a space that was traditionally out of sight and out of mind is really revolutionizing the way people can more sustainably manage these areas. Indonesia is a country that we've been working closely with. The person here in this picture is Ibu Susi. She's the Minister of Fisheries and Foreign Affairs. She reports directly to President Jokowi. And shortly after we first announced that we're working on Global Fishing Watch, she came to Google and she met with us and she said, how do I use technology like this in Indonesia? And so she's been extremely progressive. And she's the first country ever to take what was traditionally very proprietary data. So she's supplementing our AIS work with what we call VMS, or Vessel Monitoring Systems, which is proprietary government data. And what they found is that while a lot of these countries and companies have more data than they can handle, the challenge isn't the lack of data, the challenge is pulling out insights from that. And so by taking her data and running it through all of our machine learning programs, we've been able to give her back a lot of the other insights and let her and her teams and her Navy have more views into what's actually happening so they can focus on specific things instead of swimming in all of that data. When we talked about transshipments, it really does enable a scale of fishing that was never possible before. And so this is a very sobering picture in the hull of a boat in the Galapagos. And you're literally looking at thousands and thousands of sharks that have been finned and cut. And what ended up happening as we zoom out is you can see how they've been removed in different areas. These are hammerhead sharks and silky sharks. There's some tuna in there as well. And so working with National Geographic as well as many of the Galapagos conservative groups, they were able to go in, and they said that these were thousands, if not tens of thousands of sharks. This is historic. This is the biggest seizure of sharks in the history of Galapagos, for sure. And what happened in the end is the boat that they caught was fined about $6 million, and the crew is currently in jail. And the Ecuadorian Navy did an incredible job of bringing that in and then trying them in their court systems. But what they tried them for is somewhat of a loophole, because they were transporting endangered species through a marine protected area. But what Global Fishing Watch is allowing people to do is start to understand that network of other vessels that were involved in that and transshipped their catch onto this boat, because this boat itself wasn't the one that was doing all of that fishing.
So I think that's a really good point. The fishing was actually happening elsewhere in the ocean, and really what's exciting to me about this is that the high seas of the ocean is kind of this last frontier, and this area that's synonymous with like things that you can't tell is happening there, right? And so what happens is that we overfish, and all those things are caught, and all these endangered species are being caught, and it's a huge management problem. And once you can see what's actually happening there, people can start to take action and do something. And so I think it's a place where I think it's really new data is really exciting because it makes a difference.
This is another example. This is the Sanchi. This was an oil tanker that crashed with another vessel out in the middle of the Asia Pacific. And because it had so much oil and other toxic areas on it, it ignited and it burned for well over a week in the middle of the high seas. And so this was an oil spill that's on par with a lot of the other famous ones that people have heard about in the US. But because it's happening out in the middle of the ocean, it's not really getting any coverage the same way. And it's really, really difficult to estimate what the impact this will have as toxins are leaking out all over. And because we've made all of our data completely open, Reuters gone out and they started modeling what the effects of that tanker are going to be. And so they built out an area that looked at where the oil was going to spread, and then they brought in all the Global Fishing Watch data as well, and were able to say over that same 2 or 3 week period that they were able to, actually I think it's about a 3-month period that they modeled out where the oil was able to go, they could see which fishing grounds were going to be affected. And as we look at other ways of integrating Global Fishing Watch data, there's a huge opportunity to work with local markets so that you could actually see where your fish was caught and whether it may or may not have been in the vicinity of some of these natural disasters or man-made disasters as they're happening. There's another example here that's, I think, very telling. Traditionally, when new marine protected areas wanted to be created, there's often pushback from local industry and other areas. And what's happening here is there's a new marine protected area they were trying to create in Mexico. And that's this little red box in here that they tried to do. And I'll try to do this live. We'll see if it cooperates this time. One more time. And so when they went in, the industry had said, look, if you close this area to fishing, we'll lose job security, we'll lose the fish that we need to feed the country and everything else. And traditionally, this has always been very one-sided because industry has had this information, but governments and NGOs and other public interest groups have not had access to this. With Global Fishing Watch, they are able to say, okay, here is everywhere that Mexican fishing vessels are fishing. And what we're able to see is that that little red area there is less than 4% of the total fish and the total profits that are being collected by this. And a lot of the work is being done out in the high seas.
I just want to say it's really great because these arguments usually, they can start having conversations about actual numbers and things once you bring this to the table. Because before it's like people come to the table with like, no, marine protected areas are going to destroy our business, or marine protected areas are great and they're going to save the ocean. And now we can actually say, well, actually they're going to prevent this percentage of fishing and save this much area. And then that allows you to actually make progress and have real conversations.
In that case, National Geographic and Pristine Seas has a program where they work with local governments to enable them to have access to this other type of information and figure out from a scientific perspective where these policies can be done. And in the last year or two, they've actually created new 5 marine protected areas using data from Global Fishing Watch. Some of these areas are larger than California, twice the size of Germany. And we're seeing this all over the world now and are really excited about it. So one of the things that's exciting about this is that Global Fishing Watch would not have been possible 5 years ago. The satellite data didn't have the global coverage that we need. From a regulatory perspective, a lot of these vessels did not used to publicly broadcast, and we're seeing more and more pressure from that. But then finally, the computing power was never there to handle massive, massive amounts of this data and be able to scale it over an area that you didn't have to be a hardcore computer programmer to start to be able to tease out that information. And then be able to visualize everything in a simple web page that's free and public, and anybody in the world can go in and see that. And so we're really excited by the fact that 5 years ago this wasn't possible. It's just starting to be possible now, and it keeps growing and growing. And a lot of the things that you've seen, we've done all just off of kind of the equivalent of a GPS broadcast. But now the next wave is going to be looking at all kinds of satellite imagery and radar and other ones to get an even bigger sense of what extent we're fishing our oceans so we can better manage them for the future. So thanks very much, and I think we have questions coming shortly. All right, well, welcome back. All right, so we have some questions from the audience. Some of these are often the questions we frequently get asked, and there's a couple new ones in here too. So, all right, the first question is, why can't boats just turn off their AIS and you'll never see them?
They can. That's the answer. But the trick is you can see when they turn it off if they're away from shore. And so you can, and that's suspicious, and so we can highlight it. And we've done some analyses where we compare the number of days at sea for certain fleets with official statistics, and it does quite well. So this is a problem in some specific parts of the world that we have to do more investigation on, but for most of the data set, it is not a huge problem.
Okay. And actually, I think Oceana, another nonprofit that we've worked with, has recently released a report where they looked at across the globe and they said, show me examples of boats that have kind of consistently been turning off their AIS just as they're approaching protected areas or other exclusive economic zones. And we're not saying what's legal or what's illegal, but we're putting the data out there to start having conversations. And we think that's really the value of transparent information.
And to be clear, there are places where this is an issue that requires that type of attention that Oceana has brought to it.
Okay, so do you see any difference between running the machine learning models in virtual machines versus in Cloud ML? And did you get any uplift? And have you played with GPUs or TPUs?
Yeah, no, those are good questions. Cloud ML is really nice because of the auto scaling, so you don't need to you don't have to allocate all of your machines beforehand, and it's allowed us to do things much more efficiently. We have not been able to use TPUs, tensor processing units, but we have moved to GPUs, which have about 10 to 20 times more efficient, faster than doing our model on CPUs, which is really nice. It makes a big difference.
And I think what's happened is not only is it so much faster, but then it also decreases your costs because you're not running the machines for as long as you need. All right, so it sounds like you're basing this whole project off of AIS. Other types of tracking information you can use. So I think we actually touched on that a little bit in there. So governments like Indonesia are coming forward and providing their own vessel monitoring system data. And so I was actually in June of last year at the UN Oceans event. We stood up with Ibu Susi and we launched all the Indonesian data in there as well. And since then, we've actually built out a team of about 3 or 4 people that are in Indonesia working with the local government to provide them access to these tools and build the type of custom reports and tools that they need to push these further. And we also talked a little bit about how we're just starting to use a lot more satellite imagery and radar and other areas to measure what we call the dark fleet, or vessels that aren't broadcasting.
And we're actually soon going to be adding to Global Fishing Watch a layer where you can, there's another thing called VIRS, which is a satellite from NOAA that looks at night lights. And so squid fishing vessels fish with really bright lights. And so these satellites can actually see those, and we're starting to match those up to fishing vessels, and we'll be able to see, you'll be able to see that soon in Global Fishing Watch, that layer of that satellite, and so you'll be able to see those night lights. And it's really interesting. There's some places where there's boats that don't have AIS, but are fishing squid, and you can see that now in this map. So.
How can people get access to the data?
Globalfishingwatch.org and globalfishingwatch.io.
All right, that works. Just Google it.
Just Google it, yeah. It's we have released, so the raw AIS tracks, we can't release all of those because some of those are proprietary, but we have high resolution graded fishing effort by vessel and that you can by day, so you can really kind of dig down into the results of these models.
And I think you've made it available in CSVs, in BigQuery directly, so you can play with it. It's also been rasterized and available in Earth Engine, so if you want to bring it in along with sea surface temperature or depth in other areas like that, it's all in one package already.
And on globalfishingwatch.io, there's sample code and blog posts that describe each of those, so BigQuery and Earth Engine, how to access them.
Okay.
Yeah. I highly recommend using those over the CSVs, because the CSVs just give you a 25 gigabyte file, and it's much harder to deal with.
Okay.
So. And
then finally, in the last 30 seconds, what's wrong? Where are the holes? Where do you lack coverage?
Oh, no, it's perfect. So the main issue is that not all boats have AIS, and it varies by region. We've dove into this on a recent science publication. You can look in the where we supplemental materials. There's a large table saying by country, but we have documented this quite extensively. There's also some regions where AIS coverage is not quite as good, but by and large, it's a problem that we can address.
Great. All right, well, thanks so much. It was a pleasure today, and I think there's another one coming next.